We now would like to look at another property of current loops, which we're going to refer to as magnetic dipole. So let's suppose that we have a loop of current in a conducting wire. So we have a current I, and accordingly, we're going to draw a unit normal with the right-hand system. Now, this current loop has a characteristic magnetic field, which we've looked at, and I can draw a few field lines, circles around the edge, field coming up, going out like that. So here's the characteristic field lines of a current loop. And what we'd like to introduce is a quantity called the magnetic dipole associated with the current loop. So what we have is we're going to have a vector, and that vector is going to point, it's called mu. Sometimes people write this vector as m. We'll use mu. And the definition of the dipole moment is the current times the cross-sectional area of this plane. So let's make a little plane here, and we'll indicate area A, times the area A, and its direction is given by the right-hand rule. Now, this magnetic field looks very much like the field of a magnet. So if I were to draw a north-south magnet outside the magnet, the field looks similar. Of course, inside the magnet, the field is different because the field lines are moving up. And so a simple bar magnet will also identify as a magnetic moment, mu, with that bar magnet. Now, one of the key things is, why is a current loop where we have moving charges a magnetic dipole, and a bar magnet is also a magnetic dipole? Well, magnetic materials like a ferromagnet consist of atoms in which there may be one free electron in the external shell, and that electron can have two spins, up or down. So it's actually a quantum mechanical particle, but you can think classically that electron is orbiting the atom, that one free electron is like a current loop inside an atom. And so a ferromagnetic material you can think of as a bunch of tiny little atomic current loops. Now, those current loops could be oriented in different directions, but when those current loops line up in domains, they can all add up to give a macroscopic magnetic moment. And in order to understand this in more detail, we'd have to look at the magnetic properties of materials, which we'll not look at the moment. What we're going to just do is look at this simple current loop and consider this our definition for magnetic dipoles. And now we'd like to explore what happens when you put that dipole in fields, in magnetic fields.